Mr. Moore, what's going on?
Oh, not much. Just, yeah, I'm not a real big fan of the blue Kool-Aid, that blue raspberry stuff. It's just nasty. You know, I'd rather have me just a glass of water. And you know, us science teachers, we can't do anything the easy way. So I'm making my own water here.
I understand. That stuff's too sweet anyway.
What you doing? That looks good. What you got there?
Oh, yeah?
Yeah.
Well, you know, Miss Hurdle makes this famous olive spread.
I've heard of it, yeah.
Yeah, it's got olives and onions and carrots and peppers. It's real good.
Sounds delicious.
Yeah. It's even vegan.
It's even, well, you know, I'm all over that. So that sounds like a mixture of some tasty ingredients there.
Yeah.
Oh.
Wait a minute.
We might be able to do something with that.
That sounds familiar.
Yeah.
Are we supposed to talk about that?
I think so. What? Oh!
Oh!
Elements, compounds, and mixtures. Wow.
Look at that. Who knew?
What a coincidence. Well, what do we have here? I guess we've got some notes. Maybe if you're out there in real world land watching this video, you might want to take some notes on this. You might just learn something, and you might just get a quiz or a test on it. So pure substances. What are pure substances? Well, it's a sample of matter that has definite chemical and physical properties. Some examples of pure substances are elements and atoms, molecules, and compounds.
All right, so the first example of those elements, they're, as you know, a pure substance that can't be separated into simpler substances. It's the smallest form of matter. So for example, the smallest amount of anything that you can have, let's say copper. The smallest amount of copper you can have is just one atom of that element copper. That's it.
Or even sulfur.
Hey,
Look at there. Sulfur.
it's almost like we had this planned.
Almost.
Sulfur.
Compounds. We've talked a little bit about compounds here in the last couple of weeks. The examples at the top are H2O, our tasty, tasty water. NaCl, which is the salt that we put on our French fries to make them so delicious. And then CO2, carbon dioxide, something that we breathe out through respiration, needed by plants to grow. What are compounds? They're pure substances composed of two or more different elements joined by chemical bonds. They're made of elements in a specific ratio that is always the same and can only be separated by chemical means and not physically. So just to recap a couple of things, it's a specific ratio. When we're talking about balancing chemical equations, you've probably heard Mr. Moore, Mr. Marmara, Ms. First say that basically you can't change subscripts. Whenever you're trying to balance chemical equations, you can't make H2O into H3O because you're changing the compound. You can't do that. You can only change the coefficients. So, again, made of elements in a specific ratio that is always the same. Water will always be H2O. And then this part can only be separated by chemical means, not physically. I can't go in and take a water droplet and physically pull it apart so I have hydrogen in this hand and oxygen in this hand. With compounds, you can't do that.
Yeah, and you brought up sodium before, sodium chloride.
Yes.
Here's a nice big plug of sodium chloride there, donated by Ms. First. There you go.
Excellent.
Okay, mixtures. We started off talking about mixtures earlier. So they're a combination of two or more pure substances that are not chemically combined. So they're just kind of hanging out next to each other. These are held together by physical forces, not chemical bonds, and no chemical changes take place to make them. Each item in that mixture is going to retain its original properties, and they can be separated physically. So there's a lot to digest here. Let's start off actually right here, where we're combining them using physical forces. We can make mixtures. Let's take Ms. Hurdle's olive dip, for example. To make the olive dip, Ms. Hurdle would have to cut up the olives, the carrots, and simply put them in a bowl and mix them together. So when she does that, no chemical change takes place. There's none of the please excuse coughs, sneezes, and burps happening. Right? No gases are produced, no color change that wasn't expected happen. Energy is not released. None of that is going on. But what's also interesting is that each item is going to retain its properties. So the mixture overall has some properties to itself, but I can pick out individual pieces and taste each piece. So I can pick out a piece of carrot, and it's still going to taste like carrot. I can pick out an onion and still taste the onion. So each piece of that mixture is going to retain its properties. And if I don't like carrots, can I go in there and take them out?
It would take a while, but yeah, you could actually go in and pick out the parts that you don't like. That's perfect.
And that's a good point Mr. Moore brings up, is that it's not always going to be easy to separate a mixture. For example, Mr. Moore's Kool-Aid. He does not like it. He just wants the water out of there. So it's going to be a little more difficult to do that. All right, we're physically separating the dyes and the sugars out, but we'll have the water left over.
Yep, when we're done, there'll just be blue powder and sugar in this side, and over here we'll have pure drinking water. Creating mixtures. Mixtures are created by combining a solute with a solvent. A solute is an item that is being dissolved in another substance. For example, the salt in salt water or in the ocean. A solvent is an item that is dissolving in other substance. For example, when we talk about the ocean, it's the water. The salt is being dissolved by the water. The water is the solvent. Then we have a solution, which is what we call the whole thing. That's the combination of the solute and solvent together. This is my blue Kool-Aid solution. Okay? And then we have different types of solutions. We have homogeneous or homogeneous. I've heard it pronounced both ways. And we have heterogeneous. Okay? Homogeneous or homogeneous mixtures look the same or uniform throughout. That word uniform. We all know about our dress code policy. We all have a school uniform, although this year it's a lot less strict than it was last year, thank goodness. But basically, uniform is so that we all kind of look the same. If someone walks in with Ronald McDonald shoes and the big orange afro, they're going to be disruptive to the learning environment. So we want everyone to look a little bit the same, or sort of the same, so that it's not a distraction. Heterogeneous means different. You can see the individual parts. Think about like a Big Mac sandwich. You know, you got the 2 all-beef patties, special sauce, lettuce, cheese, pickles, onions on a sesame seed bun. You can see, oh, I'm really hungry now for some reason. I should be doing these after school before dinner because my stomach, I don't know if you heard that. But anyway, you can see the individual parts. The buns look different than the patties, which looks different than the cheese, which looks better than the lettuce. And again, if you're not a fan of onions, open it up, pull the onions off, no problem. Very easy to separate.
So right here we have a data chart. It might be a little difficult to see on the video, so we are attaching this to our PowerPoint presentation on our Google Classrooms. But feel free to look at this at your own time so that you can get more of an understanding of the differences between mixtures and compounds.
Can you identify the following? You will be shown a series of photos. Decide if each photo represents an item composed of an element, a compound, or a mixture. So let's review before we get started, okay? An element contains just one type of atom. If we're talking about gold, it is just gold atoms. If we're talking about sulfur, it's just sulfur atoms. It's not a combination of different things. It's just one simple atom from the periodic table. If you don't see it on the periodic table, it is not an element. Which just makes sense, right? A compound contains 2 or more different atoms joined together chemically. Think water, think salt, carbon dioxide, carbon monoxide. Whenever we take multiple elements and mix them together with a chemical bond, combine them with a chemical bond, then we have what are called compounds. And then a mixture contains 2 or more different substances that are only physically joined together. They're not chemically combined. You can separate them. Might take some effort, but they can be separated without using a chemical reaction. A mixture can contain both elements and compounds. Okay?
All right. So, here, take a moment at home. Element, compound, or mixture. What do you think about rocks? Pause this video and think about it. All right. The answer is
a mixture.
A mixture.
You can look at the rocks and you can see the grains of different types of rocks all mixed together. So it is definitely a mixture. Now we have copper. Would copper be an element, compound, or a mixture? Think about your periodic tables. What do you think?
The answer is element. As you can see on the periodic table, copper is listed as one of the elements.
I see what you did there. I see you.
Aha. Our next one.
A bag of jelly beans.
Element, compound, or mixture? Right, the answer is mixture. You can see see all the different colors. So let's say I don't like the purple jelly beans. You can easily pull out the purple ones and enjoy the rest of your bag. Maybe throw them at Mr. Moore. All right, next one.
Next we have table sugar. We talk about salt a lot. Let's give sugar a little love today. Table sugar. Element, compound, or mixture. What do you think?
And the answer is...
It is a compound. Yes, and it has a chemical formula. With a lot of compounds, you'll notice they have a chemical formula. In this particular case, C12H22O11. If you're taking a test or an EOG, that might be a clue. You see a chemical formula down here, you can pretty much bet that it's going to be a compound.
Also important to note, we've been using in class the chemical formula for sugar C6H12O6. So that's the formula for glucose, right, which is our simplest sugar. So table sugar is a larger, more complex sugar, but if you'll notice, it's basically double what the original formula for glucose is. So that kind of gives you an idea of how we can structure these compounds to become larger or smaller, but still maintain the same ratio. Those ratios are important.
Next we have element, compound, or mixture, a diamond. Shine bright like a diamond.
Let's see. What could it be?
I think it's going to be an element. Because a diamond is really just carbon. Carbon. And carbon, again, is on our periodic table of elements. So it's kind of tricky. You have to know what a diamond is. But a diamond, other than being a girl's best friend, is also carbon, which is an element on the periodic table.
All right. Try another one. Salt. We talk about salt all the time. Talked about it earlier in this video. Wink, wink. All right. I think it's element, compound, or a mixture. Ready? Here we go.
Salt is a compound. Again, we have a formula, NaCl. One sodium bonds with one chlorine, and now we have a compound, salt. Tasty, tasty salt.
And I remember Mr. Moore was talking about compounds earlier. He said that when these elements combine to form compounds, they lose their original properties. So salt is a really great example of that because it contains two elements, right? Sodium, which is an alkali metal that blows up when it comes in contact with water.
Boom!
And chlorine, which is a highly poisonous gas. Individually, those are obviously very harmful. But when we combine them chemically in a compound, they lose their original properties. Very different from a mixture where each of the original elements still maintain their properties.
Good point. Good point. Element, compound, or mixture. Pure water. Okay. Pure water. What do you think?
All right, let's see what the answer is. It's a compound, as you can see. Again, we have a chemical formula, and it has a specific ratio, H2O.
Very good.
And our last one, element, compound, or mixture, sand.
Is sand on the periodic table? I don't think so.
Let's take a look.
Sand is a mixture.
Sure.
It is a mixture. And you can kind of see, if you look at it, you can see all the different grains. You've got bits of shell in there. You've got bits of bone in there. And then you have rocks crumbled down. So yeah, it's definitely a mixture of many, many, many different things that if you were very patient, you could sit down and separate the sand into its individual parts. I would hope you would have something more fun to do at the beach than separate sand, but you could do so if you wanted to.
Definitely. Also important to note, sand does not have a specific chemical formula. There's many, many types of sand, right? We have the black sand beaches of Hawaii. Compare that with the white sands of Florida. That's because they're mixtures of different materials that are broken down through erosion. So that can also be a way for you to think about that.
Good point. Okay, and we are including with the presentation what's called a dichotomous key. And basically, those of you may be familiar with computer programming or whatnot, it's basically a flow chart. You go through and you ask yourself the questions, and based on whether you answer yes or no, they're all yes or no questions, it'll guide you down to your final answer. So if you take something, for example, like hydrogen. So you take hydrogen, and your first question is, Does it have variable composition, or is it the same throughout? No, it does not have variable composition. Is it a pure substance? Can you simplify hydrogen? Can you break it down into something more simple? No, that's an atom of hydrogen. That's as small as you can get. So again, no, and it tells you it is an element. So you can plug in, practice, come up with anything you can think of off the top of your head, and then run it through these questions, and it'll tell you whether you have an element, a compound, a heterogeneous or homogeneous or homogeneous mixture.
Right, and that is the end of the presentation. So,
That's perfect timing. I'm about ready for my glass of water here.
oh yeah,
Yeah, let's see here.
I think I might finish up Ms. Hurdle's olive mixture here.
We really do appreciate your time, and hope you take excellent notes on this. Like I said, you might see this stuff again. You will see this stuff again. And to be successful, you got to do what you got to do.